Today we're going to discuss the classic topological sorting problem. We have some set of tasks that we need to complete. We also have a list of prerequisites. For example, we might know that task A must be completed before task B. Our goal is to find some order in which we can complete the tasks. If that's impossible, we should also output something indicating that. Just so we understand the problem, let's quickly look at an example. We have a bunch of tasks. In this case, each is labeled with a character from A to G. We also have information about prerequisites. For instance, we know that task A must be completed before task C. We can represent this with an arrow from A to C. We also have all the other prerequisite pairs, each of which is shown as an arrow here. We can use this information to construct a directed graph. The tasks become our vertices, and the arrows for the prerequisites become our edges. There are two distinct main ideas to solve this problem. The first are solutions based on decrementing the in-degrees. This is a very intuitive solution that we will talk about first. The second are solutions based on backtracking in depth-first search. This is much less intuitive, but the technique can be used for much harder problems, like strongly connected components. We will go over both of these in turn. The solution based on in-degrees is very natural. The main idea is that any time we can greedily choose the next task we are going to complete. We start by looking for the tasks with no prerequisites. In this example, the two tasks with no prerequisites are A and B, which I will keep highlighted in red. Once we have identified all of these immediately doable tasks, we will choose one of them to do. So I will choose to complete task A first. And after I choose A, I will remove all the prerequisite edges coming out of it. Next, I will choose to complete task B. We again remove the prerequisite edges that are coming out of B, and now C no longer has any prerequisite edges coming into it. In other words, we can do C. So now, after completing C, which is the only doable task at this moment, both D and E become doable, and we continue to do the same thing. At any given point, we are choosing to complete a task that has no edges coming into it. In other words, we choose to complete tasks with in-degree 0. The implementation of this first solution is quite straightforward. We start by converting the edge list into adjacency lists so that we can traverse the graph. In addition, we can record the in-degrees of the vertices. Then, we create a to-do queue of all of the doable tasks. We've already calculated which tasks are immediately doable, that is, the tasks that currently have in-degree 0. Note that it does not matter what data structure we use to hold these, since we can choose what task to do next arbitrarily. We can use a stack, a queue, or even something that lets us choose completely randomly. Finally, we traverse our graph. Like all graph traversals, we perform a simple loop so long as we have more than one entry in our to-do data structure. Pop from the data structure, add the node to our visited list, and then look at the neighbors. In this case, we decrement the in-degree of the neighbors and only push them to the to-do queue if their new in-degree becomes 0. This gets us almost all the way there. There's one thing missing. What if it's impossible to complete all the tasks? This is equivalent to asking, what if there is a directed cycle in the graph? I'll leave it as an exercise to work out a formal proof, but it's as simple as checking whether or not all the nodes in the graph are visited during the traversal. Moving on, the backtracking DFS solution is a little harder to understand. We start by performing a basic depth-first search from some starting node, and whenever we reach an edge, we color it green. Eventually, we will reach a dead end. This is where the backtracking part comes in. When we have visited all of the children of a node, if it has any, we need to backtrack along the edge we came from, and we color the edge red. In addition, we also need to add the node to the back of our ordering. After backtracking to the preceding node, we go look at the next child and recurse. The green nodes at any given point will always form a directed path, and depth-first search gives us a very nice property. Whenever we look at neighboring nodes from our current node, the color of that neighboring node will always be either blue or red. And if this is not the case, and we see a green node, then we would have actually found a cycle. This example doesn't have any cycles, of course, but you could try to work this algorithm out by hand to see for yourself too. After we finish looking at everything in our search, we may still have unvisited nodes. That's because there's more starting nodes left for us to try. we have to try starting our search from every single node, not just one. At the end, we will have a valid ordering of all the nodes. To implement any backtracking DFS algorithm, it's easiest to use a recursive implementation of depth-first search. The recursive DFS function itself will have a rather complex signature. As parameters, it takes in a graph in the form of adjacency lists, a reference to the return list, a current node to visit, and the current colors of all the nodes in the graph. It returns true if a cycle is detected and false if everything is normal. This isn't the only choice of signature, but it does the job. Just make sure everything except the current node is passed by reference. Otherwise, we risk changing our complexity at the end. Let's talk about how to initialize everything. Choose some representative values for our three colors. All the node colors will start as blue. Like last time, we need to convert our list of edges into adjacency lists. For convenience, we will construct the adjacency lists with the edges facing backwards. This is a quick implementation hack that lets us get the ordering forwards instead of backwards, just so we don't have to reverse it later. Inside our recursive DFS function, we start by checking if the current node has already been visited. If it's green, then we found a cycle. If it's red, then we've already explored this part of the graph. Otherwise, it's a new node and we haven't seen it yet. Color the node green and then recurse on each of its neighbors. After we're done, color the node red and backtrack. Backtracking in this recursive implementation is very simple. Just return to the color function. As a last step, make sure we're doing the backtracking from all possible nodes, just so we don't miss anything, as we did in the example. There's a lot of implementation choices here. Your preferred implementation might use a completely different signature for the recursive DFS. It might have shorter code, and it also might not even be recursive. A more industry quality version of this particular implementation could use a class to hold all the references being passed around in the parameters. You can also hide the class in an empty namespace. Implementing this is a good exercise if it's something you're interested in. Both implementations are linked in full in the description of this video if you want to check them out. Bye!